if I can do it from downtown. Oh, fell short. Now it's going in. No. You want to try? You're gonna make it. Boom. Oh.
I made it into ankle.
Yeah. Okay, I got 2 tries. You get 2. I'm gonna try you. Boom. Oh man. How does it bounce off of the rim there? Oh man. That was unlucky. It happens. Shoot. Uh-oh. I better do my last attempt for today. You can start. Yeah. You have trouble reading that?
No.
Okay. Oh, we digitally have Caleb over here. Hello, Caleb. You may chat with me in the chat log if you have any questions. Also, Caleb, we're taking a quiz. So if you could email me the quiz and your response. Hello, how you doing? If you can email me your quiz response, that would be great. Try and do it in a relatively timely manner. So it's kind of like you're really here taking a quiz.
Is that last value in RT, is that E divided by 2?
E divided by 2 times cosecant of t. Good morning, Ira. Good morning. We're taking a quiz here. 2 problems.
on that last value, that's an E.
That's an E over 2 cosecant of t. Guys got like around 2 more minutes. That should be enough. If not, let me know. I'll give you like another 2 minutes if that's not enough. Okay, if you guys need 1 more minute, let me know. If you're done, I'll come collect it.
Mark.
Okay. Good work. All right, moving on to 10.2. This stuff is really cool because now we're finally starting to do calculus, right? What was calculus anyways? It was using limits to define derivatives and then defining integrals after that. Because of this quiz, I don't know if we'll get to integrals, but I'm going to push it and try. If not, we'll talk about the integral part on Monday. By the way, that was the cone. Remember we were trying to come up with the cone and I didn't know how to do it? That was the cone. Yep. So I'll post the solutions to the quiz as well. So 10.2, derivatives and integrals of vector functions. So for some r of t, we define the derivative of r of t to be r prime of t, just like with normal functions. And if our r of t was defined to be some vector having component functions like this, okay, then r prime of t is just this. Simple as that. Very, very straightforward. The derivative of the vector function is just the derivative of each of the components. That's it. Okay, but this is the same thing as the limit as h approaches 0 of some r of t plus h minus r of t, everything over h. Here's your visual picture right here. Let's say we have some arbitrary curve C. Here's my, let's say our r of t. Right? And then the parameter t, it varies, right? So as it varies, the vector will point at different parts of the curve. So let's add just a little bit, some h, some non-zero h, and evaluate it. So that's some r of t plus h, where h is a really tiny number, right? And we're going to make it approach almost 0. So t is some tiny number. We evaluated r of t. It points at this point right here. Then we evaluate r of t plus some tiny amount of change. It moves it a tiny amount on the curve. And then we create a vector that connects these two. Okay? That vector that connects these two by vector addition is this numerator. This right here is r of t plus h minus r of t. Okay, that's just the numerator. Now, what happens when we go from this just numerator to this complete fraction is we then multiply this entity by 1 over h. So we scale it by 1 over h. Okay, so that's when it gets scaled, and that represents some point over here. So that's this guy right here, the scaled version. And it doesn't look like it's scaled, but if this was that much, maybe this is scaled and shortened or something like that. It's not drawn very well, but your book draws it really well. So reference the book for that. And so the derivative, r prime of t, is really just like a tangent to this curve. So r prime of t over here would just point like this. And r prime of t would just point like that. So it's just a vector analog of the tangent to like some x, y. You have some curve and you're like, okay, that's the tangent line, right? Now it's in 3 dimensions. So we still have a curve in 3D. The curve actually looks no different than this in 2D. It's just now embedded in 3 dimensions. And now, because we're in 3 dimensions, we'll use vectors to define the tangent vector. There's still a tangent line, and we'll talk about that, but you can define a tangent vector now. We want to start doing everything with vectors. Okay. The derivation is very neat. Okay. So then once we get our R prime of t, that divided by its own magnitude gives us our unit vector in the direction. Okay, so this is a new definition. This capital T is like the unit vector of the tangent vector. So you get a tangent vector at some point, and then you can like unitize it, make it a unit length. So let's give an example. Let's say R of t is equal to the quantity 1 plus t cubed, t e to the negative t, and sine of 2t. Okay. Let's take the derivative of this function. What is R prime of t? Well, you guys are very astute at taking derivatives already. Just treat each of these components as a function and take ddt of that function each time. So ddt of this thing, derivative of 1 is a 0 because it's a constant. Derivative of something, a polynomial cubed, is you bring the 3 down, t to the 2. Get that 3 there. That's it. Over here, this is a product of two functions of variable t. So you have to do the product rule, okay? So when I take the derivative of t, it just becomes a 1. So this becomes e to the negative t. And when I leave t alone, take the derivative of e to the negative t. That's just e to the negative t times the chain rule d dt of negative t, which just becomes negative 1. Right? And then sine of 2t is the derivative of sine is cosine, but then ddt of the inside function, 2t, so it becomes 2 derivative of sine is cosine of 2t, just from the chain rule. And then factoring out at e to the t, we get 1 minus t over here, and then 2 cosine of 2t. That's just one example. Let's do more examples. What about this one? Let's say r of t, I define it to be t cosine of t, t squared sine of t, and e to the negative t. What if I want to discover what r prime of t is? What is r prime of t? Again, take the derivative of each of the components. Okay, so the first one, when we take the derivative of t, it becomes 1. Cosine of t, we leave it alone. Plus, now we leave t alone, take the derivative of cosine. Derivative of cosine is negative sine. So then we just get, this is a negative t sine of t, right? Derivative of cosine is negative sine. So derivative of cosine of t is negative sine of t. But that t comes along for the ride and it gets a negative on it. So this is why this becomes this. And then next we move on to this t squared sine of t. When I differentiate t squared, I get 2t, and that sine of t comes along for the ride. Plus, now I leave t squared alone, and derivative of sine is cosine. So cosine of t comes here. Next is our beloved negative exponential, e to the negative t. That's just derivative of e to the negative t is just e to the negative t times ddt of negative t, which is negative 1. So this becomes negative e to the negative t. And that's it. I could, just instead of saying plus here, remove this right here, and I can just say minus. Same thing. Making sense? Good. So this stuff is not that bad, right? It's not that bad. It's just differentiating 3 different functions instead of 1 function. You have your product rule, chain rule, quotient rule, all that stuff applies. Okay, so let's talk about this function right here. This vector function, square root of t into x, 2 minus t into y, and 0 into z. Your book shows you, so it says sketch, and then it says sketch R1 and R prime of 1, and it generates this picture for you. Here's your x, here's your y. It generates this picture for you like this. Here's 2, here's 2, here's 1, here's 1. So this is at 1, 1, and this is the vector r of 1. And then it shows you the tangent vector like this, r prime evaluated at 1. But it doesn't tell you how did you come up with this picture, does it? Of course, Maple could give you the picture. Or you can create an R of TT table. Okay? Just for your information, the way this graph got created. And notice there's no Z here. It's in the XY plane. It's only represented in R2Y. Yes, the Z component is set equal to 0 permanently. So this is in R3, but we can just think about it as just in R2. So look, for like t equals 0, t equals 1, t equals 2, t equals 3. I've computed these values for you. You get 0, 2, 0 when you plug it into R of t. You get 1, 1, 0. You get root 2, 0, 0. You get root 3, -1, 0. And so for various inputs, so 3 would be here, and the output is down. So for various inputs like 0, it starts at y value 2, z value 0. Everything has z value 0. So then at 1, it's at 1. That's why it's over here. And then at 2, it's going to be at root 2. But look, the x is at root 2. The y is at 0. So that's why you get that graph here. Because the y, this is the y-axis, this is the x-axis, this location when its x-intercept is going to be root 2. So that's why the graph looks the way it does. They're just plugging in values for t and evaluating r of t. But let's talk about how those vectors are formed, r1 and r prime of 1. Well, let's just find what r prime of t is in general. Well, square root of t, the same thing as t to the 1/2 power. Bring that down. Minus by 1, you get that. Derivative of 2 minus t, just a -1. Derivative of constant is 0. Derivative of negative t is -1. And derivative of 0 is just 0. So r prime of 1 is just evaluating 1 here. So this 1 times 1 to the -1/2, -1, 0. This is 1 over square root of 1, which is 1 times 1/2, which is 1/2. Boom. This is what our r prime of 1 is. And similarly, our r of 1 is evaluating it here. Square root of 1 is 1. 2 minus 1 is 1. 0, 0. Okay? So this is our prime of t evaluated at 1. This is our prime of, or no, that's our prime of 1. This is our r of 1. So here's our prime of 1. It starts at the origin and it points at 1, 1. Notice 1, 1, 0. And then our prime has to be at the location this is ending at, and it's tangent to the curve. And so notice, boom, it is tangent to the curve, and it actually beautifully points in the appropriate direction. Notice that its x component is like 1/2. Its y is negative. It's really encoding like a slope-like phenomena in its values. Notice how the negative component and the y is making it go down. The positive component and the x is making it go to the right. So that's how you do those things, how you sketch and think about them. And how you come up with the curve is like that. I'm sure you can let Maple do that as well, right? Maple could do that, but I'm a theoretical guy. I don't do computers. Even though computers are very powerful tools. I don't really like them very much. I'd rather avoid computers. The computer science majors in here are probably gasping. They're very powerful. Don't get me wrong. Artificial intelligence, it's going to probably rule the world. You know what? But I feel like a human mind has something that there's no way you can model. I think the human mind and our creativity, it cannot be surpassed if you work at it. I know some really strong Terminator cyborgs that can do calculus in their heads, and it's really easy for them. Geez, I'm ready to box one of them dudes. They're gonna try and take over the planet. Okay, now let's talk about the tangent line. We were talking about tangent vectors, but a vector can help you define a line, right? If a vector is parallel to that line, you can create a vector representation of the line, right? That whole r is equal to r naught plus vt stuff. Remember that stuff? Yeah. So let's find the tangent line. Find a tangent line in parametric form to the helix with the following equations. Okay. And we want to evaluate at this point in three-dimensional space. So again, to come up with why this shape looks the way it does, you can create an RT table. And I've done this for you guys in advance. Let's say this is at pi over 2. Then this becomes 0, 1, pi over 2. Let's say this is at pi. Then this becomes -2, 0, pi. Let's say this is at 3 pi over 2. Then this becomes 0, -1, 3 pi over 2. Let's say then this is at 2 pi. Then this goes to 2, 0, 2 pi. We're just evaluating r of t is equal to this. Plugging in various t values, and what's popping out is this. Bloop, 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 bloop. And so what's cool is it creates a cylinder. Well, it doesn't create a cylinder. The motion of our particle, if you will, are what we're trying to like define. The motion of this object is basically moving on the surface of a cylinder. Okay, it's not generating a cylinder, it's moving on the surface of the cylinder. Okay, and so it starts out right here. This is its starting point, 2, 0, 0. And it'll move to, now it has 0x, maybe it has 1y right here. And now it's moved up pi over 2 in the z. So it's right here, so it moves like that. And so then it's gonna wrap around for these various values. But the problem wants us to find a tangent line at this point right here. And this is one of our points. it's when t is equal to pi over 2, right? This is a t. So I can delete this stuff because you see it now. It's in your brain and it's in the video. Recall the vector equation of a line. Okay. Now notice that r of t is equal to r naught plus vt. So what is our r naught here? It's our starting point, isn't it? And it's right here. Our r naught is this vector. We'll find out what v is shortly. But why is this true? Well, the tangent vector starts at that point and points in the direction tangent to the curve, right? So our tangent vector is going to be right here, pointing in the direction of the curve, right? And then we're going to create a tangent line based off of that vector. So just like last time, how the tangent vector was at the point that we were talking about and then pointing tangent to the curve, that's what's going on here. So our initial r naught is where it's at. Just like how in that function earlier. First, the function pointed at the point on the curve, and then the tangent vector, the vector function pointed to the point on the curve, then the vector tangent pointed and the tangent on that point on the curve. Okay. So our initial starting point, our r naught, is this. What is our v? What's analogous to our v here? This is a 2, this is a 0, and this is a 1. Why am I putting that up there?
The coefficient of the r, t.
It does relate to that. You're very, very close. It has to do with the coefficients of r of t evaluated at what? Zero. Well, so our t here, it just remains a t, right? So what we want is a tangent line that goes through 0, 1, pi over 2, and which is parallel to our r prime, right? So this comes from the fact, it comes from r prime. So I actually can rewrite this equation like so. You know what I'm saying? So now, actually, we can evaluate r prime of t. First, we can discover what it is in general, right? So derivative of cosine is negative sine. Derivative of sine is cosine. Derivative of t is 1. So now our r prime, our t is set to what? Excellent. Remember that r of t table? We discovered that t, which is z, is pi over 2. So we evaluate this stuff at pi over 2. And that's going to give us this tangent vector on the curve. It's going to give us, what is its components? It's x, y, z. What direction? I, j, k. Okay. -2 sine of pi over 2. Cosine of pi over 2. And a 1. Notice that our prime of pi over 2 is then equal to, well, this is a 1, so this is -2. this is a 0, and that's a 1. Notice that that's what these values are right here. So our r prime of pi over 2 is behaving like a v. Remember I told you this was like a y is equal to a mx plus b back in pre-calc. This m, this v, this r prime of t are all functioning like slope. And so when we evaluate r prime at pi over 2, we're actually calculating what is the slope at this location. Because it changes, right? At different parts of the curve, the slope changes, just like on any curve. So that's why we're doing all these things that we're doing. So notice that when we do component-wise addition, can I fit it here? 0 plus a negative 2t is just a negative 2t. 1 plus a 0 is a 1. And pi over 2 plus a t is this. You guys see why I'm doing that? The t is a scalar, right? It can just scale each of these components. So I could have written this as negative 2t, 0t. And then I add them component-wise. This component plus that component gives me this. This component plus that component gives me 1. This component plus that component gives me pi over 2 plus t. So now we have a parametric equation for this vector right here. That's this vector right here. But we wanted the tangent line. And we got it. We wanted the tangent line and we got it. So just remember, if it's asking you for a tangent line at some point, don't forget this. This is your best friend with lines. Understanding this and how it relates to actually is the same thing as this. And so that is your best friend right there. Going down to the fundamentals. So here's a theorem that tells you all the properties of the differentiation properties with vectors and dot product and cross product. Yes, Caleb, that's right. He's talking to me on the chat. I just realized he said something. So ddt, oh wait, I have to define what I'm talking about. Let's say u and v are differentiable vector functions, and that c is a scalar, and f is a real valued function. So we can say these things. T of two vectors being added to each other is just this. The derivatives being added to each other. ddt of a scalar scaling the vector is the same thing as scalar scaling the derivative of the vector. There's a third property. ddt of, this is very interesting. This one is very interesting. The function f of t times like your vector, what does that do? Because a function is not a vector, right? So how do functions multiplied times vectors interact with the derivative, the differential operator? And it just does the product rule. Very interesting. It's very interesting. One will have to go prove it to see why. Us mathematicians are always got a chip on our shoulder. We're always acting like we got something to prove. Okay. So 4. About ddt of u dot v. This is our dot product, okay? So how does the derivative interact with the dot product? Amazingly and conveniently, it interacts just like multiplication of functions did. So multiplication of functions, f of x times g of x, when you take the derivative of that thing, it'd be f prime times g plus g prime times f, right? Now the dot product is doing the same thing. U dot v, when they're vectors, you get u prime dot v plus v prime dot u. You have a question? Anyone have a question? Okay. It's very interesting that this is happening. It's very interesting. It's making me want to stop lecture and just go prove it and come back. No. Yeah. Now let's see, how does it interact with the cross product? Amazingly, again, it does this cool stuff here. I better have them in the correct order, though. Oh. Nope, I just reproduced the same thing here. Gotta have them in the same order. Why am I tripping about the order here? Well, it's because in general, u cross v does not equal v cross u, right? Namely, u cross v does equal negative v cross u. So they don't necessarily commute, but they do something relatively simple. So that's why I couldn't put the u prime here, because it's not necessarily true. So you got to be careful. But that's really amazing that the cross product is behaving like a normal multiplication of functions and so is the dot product. That's incredible. You guys know that makes our lives a lot easier, right? There's no interactions that we have to like newly get familiar with. That's incredible. And here's another one, ddt. This one's really cool. Okay, you have a vector evaluating a function. Is that possible? Well, yeah, a function f of t, it's a real value function, right? You give it a t, it spits out another real value parameter, maybe t prime, something different, but it's still a real number. And then this vector knows how to take in the real number and output information. So this is completely valid. And amazingly enough, you get something analogous to the chain rule. You get u prime of f of t, okay, multiplied times the derivative of f of t. So it's like a chain rule, a vectorial chain rule. Incredible. As a mathematician, I'm like in awe. I just think this is so gorgeous that this new mathematics that we've developed, the dot product, the cross product, the concept of a vector. Look at how beautifully it's behaving like functions were in just Calc 1 and Calc 2. It's behaving just like those functions were, which is really good. It's really good. Because the mathematics that applied to what we had talked before now translates to this mathematics. See how much, oh, I can introduce integrals now. Integrals. Integrals of vectors. Okay, let's define the integral from a to b of our vector function r of t dt. Just like we defined an integral before. It is an infinite sum of rectangles, right? What did you call those? Riemann sums. It's an infinite sum of all those. But now the rectangles don't form in R2. The rectangles can form in R3. And they still will be rectangles because the vector defines a curve. The vector defines a line. It can be squiggly, it can go crazy, but the vector still defines just a line. And so you can then create rectangles. It's defined as the limit as n approaches infinity of the sum I is equal to 1 to n of our vector function at ti star delta t. And that's just from your familiar Calc 1. Really, each of these terms for each I is just calculating an area. And you're summing all of the areas. So, you know, so the first one is R of T1 star delta T plus R of T2 star plus delta T. Really, this is an area because when you function the vector, when you evaluate the vector at T1, it gives you some type of like height, some type of altitude. And your delta T was like your delta X. Now it's your delta T. Is functioning like a width. Width times height gives you area of a rectangle. So we have to stop. But this is where we're going to have to start up next time. Announcement about solutions to homework and homework feedback. I have to leave town immediately after class today, and I'll be back Saturday night. So all of Sunday, I'll work on creating solutions to 9.4, 9.5, 9.6, and 9.7 and upload them for you guys to see and give you your homeworks back on Monday so that you have them to study for your exam on Wednesday. I don't feel super bad about not giving you access to the solutions yet because as you guys may know, the internet is a wild place these days. And you can find answers to problems, right? Yeah, maybe. It's okay. It helps you learn, right? But, you know, make sure once you're accessing that information, you've attempted to solve the problem, like giving it a really long attempt. And the longer you get stuck, the better of a mathematician you get. So whenever you're looking up the answers or whatever, that's completely fine. That's part of learning. Make sure that you understand them. Because once you write that down for like a homework or something like that, if you don't fully understand that, then the test will get you. So make sure you understand it, okay? And if you don't understand it, send me an email, come to my office hours. I would love to help you guys out. Ask me in class, ask me before or after class, okay? So this first test should be fun. It's not gonna be like the difficult problems in the text. It won't be like that. It'll be fair problems that can be done in, how long is your lab period? 2 hours? Okay. I'll make it to where the test should be able to be completed in an hour and a half. That way you can have 30 minutes if you'd like to review your answers and make sure you didn't forget to carry a minus over and stuff like that.
9.7 is still due on Monday, right?
We can extend it to Wednesday if you'd like. You can turn it in.
Monday's fine. I just wanted to make sure it wasn't due today.
Yeah, no, that's fine. Yeah, actually, all homework for the test can be due on the day of the test, if you'd like. You just won't get the feedback if you do that, right? You won't get the feedback if that happens. But yeah, I just want you guys to be successful. So keep working hard. Just letting you know. Okay. Nice. Talk to you later.